Hi, so my name is Maria. I work with Neo4j as an information developer, and that is really just a fancy word for a tech writer, which is what I do in my regular day job. So if you have ideas or feedback on our documentation, I welcome you to contact me about that in particular. I also have a background as an IT project manager and as an Oracle DBA. And on the right-hand side, you can see what I do when I'm not playing with graph databases. The agenda for today assumes that you are completely new to Neo4j. That's the reason for the little disclaimer picture there. I'll go through a brief history of graph databases. I'll talk about graph thinking, graph data modeling, how to import data into Neo4j, and how to get started in general. So a brief history of graph databases. We at Neo4j, we believe that everything and everyone is connected. And here we mention a few domains such as people, companies, countries, sciences, technology, software, and criminals. And it's interesting to understand how data is connected within those domains, but it's also very interesting to see how data connect the different domains to each other. And Neo4j exists to help the world make sense of data. The theory of connected data is not something new. On the contrary, graph theory dates back to the 1700s. The people of Königsberg entertained themselves by trying to figure out if they could pass through all the parts of the city, and while doing so, passing every bridge once and only once. And Euler solved that problem and publicized it in 1735, and it turns out that that is not possible. So the mathematical field of graph theory is old and mature. And also in modern times, say the last 30 years, this area of research has been very active. So let's take a leap to more recent history. On the left-hand side, we have some of the market leaders from the 90s, and they were successful in a static world. Data was being collected, but not very fast by modern standards. And the data sources were structured, think tables and relational databases. What, for example, AltaVista did to become the most popular search engine was that they created the best indexes over web pages. And then came Google, and they didn't become the de facto search engine by building bigger and more comprehensive indexes over web pages, but instead they decided to model the internet as a graph. And while the information on the individual web pages are still important, after all, that's what we're searching for. From a search perspective, the hyperlinks to and from the page is at least as interesting. So it's the quality and the quantity of a page's relationship that determines the relevance of a search result. What this slide illustrates is that graph databases have already transformed industries. The fine companies on the right-hand side have developed their own proprietary database, but those solutions have not been commonly available. So Neo4j is a platform that makes that graph technology generally available. Neo4j is a native, internet-scale native database which executes connected workloads faster than any other database management system. Okay, so let's stay with the graph platform picture for a bit and break this down. What does that mean? Internet scale means that Neo4j is a database that has all the qualities that you expect from a database. We guarantee the integrity of your data and provide functionality for security of your data. Our enterprise clustering functionality provides you with load balancing features, and they are generally good out of the box, but they also allow you to direct traffic in patterns specific to your use cases in order to secure large-scale performance over geographies. What does native graph database mean? Well, as graph databases become more and more popular, some players in this market are mimicking a graph database by putting a graph database layer on top of their legacy database. And we like this because it helps us spread graph thinking, the mindset of modeling your data as a graph. However, with this solution, you miss out on one of the most important features of a graph database, and that is a database designed for connected workloads. I'll go into this in more detail in a bit. Now for the connected workloads. So there are many databases out there, and each model has a use case or a method of use that they are particularly good at. And while we're in love with our database, and are convinced that it can be used for many use cases, what we truly excel at is the connected workloads. In cases where the connections in the data are of importance, Neo4j is the most sensible choice. I mentioned before that Neo4j comes with a mindset, where graph thinking is all about considering connections in the data as important as the data itself. Neo4j also comes with a rich ecosystem. For example, we have a large number of partners, trained professionals, and a very active and vibrant community. So what is graph thinking? Let's zero in on the mindset part. I'm going to illustrate this graph thinking with a real-life example from my own life. This will show you how we think in terms of graphs. I'll return to this example further on. So I have a very good friend, let's call her Anne. We met when our sons were in preschool and they became friends. There was also a father, Cody, although we never met him because he lives in the US. Then Anne met Dan and the picture became more complicated because with Dan came Elizabeth, Dan's ex-wife, and their two children, Chris and Carrie. And after a few years, we also got to know Carl and Ben, who are the children of Dan and Anne. This real-life example illustrates our take on graph thinking. When you have an idea, what you often do is you grab a marker and you go to the whiteboard and start drawing. Oftentimes, what you intuitively draw is actually a graph. What is so unique about Neo4j is the whiteboard model then becomes the physical model. Of course, we may enrich it with properties and constraints in order to enforce our business logic, but essentially what the programmer and their business counterparts see is the same thing. And those of us trained in the relational world are used to a cognitive gap between business people and the people who know the domain, and the developers who know the IT systems that support the domain. Oftentimes you have entire interpretation layers between those two with business analysts and others. And with this model, you lose out on the common view and the easy communication. And ultimately, the applications become rigid or even stale. On the other hand, when the logical model and the physical model are the same, we get easier and clearer communication and better agility. We get better collaboration between business and developers. Before we go into any more detail, I'd like to introduce you to the formal property graph model. So remember Dan and Anne? Here is how they can be modeled with the help of a graph. We have entities that we call nodes, and they are drawn as circles. Nodes can have labels. In this case, we're using the label person. The labels help us shape the domain, and a node can have 0 or many labels. And we relate the nodes to each other using relationships. A relationship has exactly one relationship type. A relationship also has a direction. And the questions that we need to answer decide whether the direction of the relationship is relevant. So here we see that Dan loves Anne. The direction of that relationship is important. But Dan is lucky because Anne loves him back. Dan lives with Anne. When we store this relationship in the database, it will have a direction. However, when we query it, we don't have to care about the direction because we know that if Dan lives with Dan, Anne also lives with Dan. We also see another node, a car, that has a different label, a car label. And here you also see that both nodes and relationships can have properties. The properties are key value pairs that are used to describe the nodes and the relationships. And that leads me into Cypher. Cypher is the graph query language. It's the sequel for graphs, if you like. Cypher was invented by Neo4j, but it has been opened up and is now managed collaboratively. Anyone can join the project, and all the details are available at opencypher.org. The formal semantics are being defined in collaboration with the University of Edinburgh. And Neo4j, or Cypher, was specifically designed to be very visual and intuitive. And it's declarative, meaning that you express what you want to achieve rather than how to achieve it. So back to Dan and Anne again. And let me show you what we mean when we talk about Cypher being ASCII art. We have the nodes and the relationships. And the parentheses around Dan and Anne symbolize the node, the round shape of the nodes. And the relationship between them resembles an arrow. We place the labels and properties inside the node declaration. So here we have a mini graph in ASCII art. And when we want to create this structure in the database, we simply put a create in front of our mini graph. Much more useful than the create statement is the merge statement. I will be using that further on and I'll explain it then. Now I would like to illustrate the somewhat technical term index-free adjacency. I've probably stolen this example from a blog by Dan McCreary. Imagine that we have in baking, and I would like to share some with my friend Anne. These are the steps that I can take if I enjoy index-free adjacency. I walk at the door, I turn towards Anne's house, and I walk directly over to her house and give her the hot apple pie. And she loves it. Happy ending. How would I have done this if I had lived in a non-native graph database? These are the steps that I would have taken. Walk out the door, walk downtown to the library where they have a service that tells me how to get to places. When I get to the library, I take a number. When my number comes up, I get called by a search agent. The search agent has a list of all the people in my town sorted by the address. They search the list and finally give me GPS coordinates for Anne's house. I take these GPS coordinates, enter them into my GPS and follow the directions to Anne's house. When I get to her house, the pie is cold. In a database without index-free adjacency, each time you want to evaluate a relationship between two entities, you have to do an index lookup. Also, the cost of the index lookup itself depends on the size of your database. You have to take a walk downtown to that central service, so to say, and the agent may have to find Anne in 1 or 10 books, depending on the size of your town. The cost of traversals over relationships increase exponentially with the number of traversals and the size of the database. You can do fine with up to 3 hops, but after that, your database is bound to break down. To manage this situation, you will have to start employ denormalization and data warehousing techniques, which have their own sets of challenges. When you do the same thing in a native graph database, you still have to use an index to find the first start node, but every traversal after that has a fixed cost, and it's independent of the overall database size. In our neighborhood story, the cost of going to Anne's mother's house with another pi takes just as long as it took to go to Anne. And it is independent on whether I live in a village of 300 people or in a city of 3 million people. Let's go over to graph modeling. We'll touch on a few different things. So I have my history in relational databases, so I'll touch on how to get from relational to graph, about different ways of modeling, something we call refactoring and inference, which are two important terms when we do graph data modeling. And then I'll show an example of a social recommendation example. So in a relational database, you describe your domain with tables. We can see that the important entities as table names. So in this case, I've reviewed a few restaurants on Yelp. So we have a person table, a review table, and a business table. The interesting data, such as the individual person and the businesses they have reviewed, are stored as table rows. Here is how this could look in the graph model. You see that the individual rows are created as nodes. So in the relational world, we sometimes talk about the number of rows as a measure of size. And in the graph world, we would talk about the number of nodes. The foreign key relationships and the join table are materialized as relationships. The domain is shaped by putting labels on nodes. One difference to the table model is that one node can have many labels. But in the table model, each data element can only belong to one table, unless you start denormalizing your model. Columns or tables are used to describe the main data further. But in the graph model, these are stored as properties, both on nodes and on relationships. So now, as you see, I've switched to a different tool for illustration. It's very handy for quick and on-the-fly modeling. It's still on a private website of one of my colleagues, but it will soon make it into the product and be fully supported. So one question that we often get when we talk about graph data modeling is, what's the best way? And our answer is always, it depends on the question. If you're trained in traditional data modeling, that may not be the answer you're after, because there is a theoretical best way and you're used to striving for the normal form. But here I will illustrate a simple case of why the answer is different in graph data modeling. So Dan has adopted Thomas. So socially and legally, he's the only father of Thomas. But he still has some relationship to him, right? Here we're recording that in a property type of bio on the parent relationship. And this graph has all the relevant parent-child relationships and all the important information known at the present time. This is the same data model slightly differently. Assume, for instance, that we're building a system for research on the effect of nature and nurture, and that this is a tiny sample of a much, much larger population. In order to assist performance, we may choose to make relationships more specific. Since the database is optimized for traversal, it's much more efficient at singling out the right relationship and follow that. It gets slower if it must stop on each relationship in order to evaluate its properties before continuing the traversal. In the very extreme case, we could move all the properties into relationship types. The other term that I wanted to mention is inference. Inference is a technique to enrich the data. So we deduce information from the facts that we have. Some of this is hard facts, such that Carrie and Chris are full siblings, as are Carl and Ben. But what about the relationships between Carrie and Chris and Thomas? We can model a relationship here, and the assumptions that we make are strongly tied to our use case, or for that matter, the theory that we wish to test. This is a different example where I want to use my social graph for recommendations. My friends Anne and Diana are also active on Yelp, and when I travel to New York, I want to find restaurants that I like. The assumption is that I will probably like what my friends like. Here is how I could find the recommendations that I'm looking for. Step by step. I want to search for the pattern where a person who is a friend of mine likes a restaurant that is located in New York and serves sushi. Here with the dot notation where I return rest.name, I will get a tabular result rather than a graph. When I created this data, I had made a typo. So when debugging it, I rewrote the query so that the pattern would become even more obvious. This is an equivalent query to the one above. Cypher very kindly told me that I was about to make a Cartesian product, which is a horrible thing in a large database. And that is regardless of whether you do it in the relational database or in a graph database. So even with Cypher, we have to avoid being stupid and perhaps do some query tuning once in a while. Here is the Cypher that I wrote to create the structure. You can see that I basically just draw what we have already modeled on our whiteboard. Also, I'm using the merge clause, as I mentioned earlier, rather than the create clause. The merge clause works like this. It first looks for the pattern in the database. If the pattern exists, it fetches it for you. If the pattern doesn't exist, it creates it. So it's a kind of upsert. When I use merge, I can keep adding to my data script and keep running it without having the risk of duplicating my data. However, even for a tiny data set like this, the typing quickly gets tedious. So now we're going to look at some other ways to get data into Neo4j. Import the data. First of all, I recommend that we download and install Neo4j Desktop. It's available for free at the Neo4j website. Once you've downloaded it and installed it, you click Manage, and then you do Open Browser, and then you get access to the Neo4j browser where you do all the querying. I'll be illustrating the import with the help of the Yelp dataset. For those who don't know Yelp, it's an online site where you can rate different businesses and write reviews, etc. Yelp have made their dataset or part of their dataset open for learning and for research, and there have been many academic papers written on this dataset. So it's available on yelp.com/dataset. And what I have used here is the JSON format. And here I have, again, probably stolen from my colleague, Will. And you can see where he has made his scripts available. So I've converted the JSON files into CSV files. Just for interest, this dataset is also available in SQL, and this is the result when I tested importing that database into a MySQL database. Right, back to Neo4j. So once I've converted the JSON files into CSV, I go to the Neo4j Desktop, and I put it into the import folder. So load CSV is a Cypher-based class to import data. It's using transactional rights, and it's good for smaller data sets, such as up to 10 million nodes and relationships. It reads from CSV files, but it can also fetch those CSV files from somewhere on the internet through HTTP. And when you use load CSV, you get access to the full capabilities of Cypher. You can create and update graph structures. You can do data conversion, filtering and aggregation, and you can destructure the input data that you have in your CSV files. I will be using the transaction size control later. I'll point it out to you, but it's a mechanism to avoid that you load too much into memory and get an out of memory exception. You can use load CSV with Neo4j browser or Cypher shell. And when you start exploring this, I recommend that you have the Cypher ref card handy, and the URL is right there. So now I have this file called user.json.csv. And the first thing I do is I inspect the data in the file. And this is the class that I write and the result that I get. And I'm limiting to 10 rows so that it won't get too slow. So you can see how the data in this file is structured. Before I do anything, I create a constraint on something I call a Yelp user. By doing this, I also get an index on the Yelp user ID, and that is helpful for performance. And here you also see that transactional control that I was talking about, the using periodic commit. It reads lines of 100 at each time, and then it makes a commit, so it doesn't collect all that in memory. And when I was doing this, I had a little bit of a data quality problem. So now I had to refer to the data elements by number, where it says line and then the number 15 in brackets and the number 21 in brackets. If you have a better sample, you can also refer to the lines with dot notation if you have headers in your file. So I noticed that there are not only users in this file, there are also friends and fans. And I've been using an unwind in these clauses. I got the inspiration for this from a blog by my colleague Mark Needham, and you see the URL in the bottom of this slide. So after I've run these 3 statements, I actually have a data model. And you see it on the right-hand side. Without having created anything such as a schema in the database, I have actually created it through my data. And I see here that I have a Yelp user, and a Yelp user can be a fan of a Yelp user, and a Yelp user can be a friend of a Yelp user. Then I went on to the business data. Similarly to the user, I started by creating a constraint on a business ID. And then I looked at the business file. And then I started importing the business file. And here, I only import the businesses as they are. I put ID, city, name, and state as properties on the business nodes. And the final thing I've done here is I've imported reviews. I start by putting a constraint on the review node type, and then I look at the review file, and I find some structure in there that I will want to use. So I merge the review where I use the idea, the review text, the number of stars, and the date of the review. And I've seen that the user that made that review is in that same file. So I merge on the user. If the user exists in the database, I fetch it. If it doesn't exist yet, I create it. Same thing with the business. I merge on the business. If it exists, I fetch it. And if it doesn't exist, I create it. And then in the 2 final lines of this statement, I create a graph structure. I make a structure where the user wrote a review, and I made the review as a review of a business. And again, when I call the db.schema function, I can see the inferred schema. So now I have a theoretical model where I have a Yelp user, a review, and a business, and some relationships between them. I'm also quickly going to show you how you can get ODBC to work with your SQL database if you have one. And I've used MySQL locally on my database. And in order to connect Neo4j with MySQL, I had to find a MySQL connector. I also made sure when I downloaded Neo4j Desktop that I install the APOC library. And yeah, as you see, I have also the graph algorithms library, but we're not going to use that now. So when you use JDBC with your SQL database, it's using, you need to use a library within the APOC library. And you can access any database that provides a JDBC driver. It executes queries, and those results are turned into streams or rows. And then you use the rows to update or create graph structures. And here is how I use JDBC to access the MySQL database on my computer. You can see on the right-hand side how I can inspect the data from the MySQL database. And here we have queried the MySQL database for some actual data. And here I actually use the data from the MySQL database to create this data into my Neo4j database. If you have larger quantities of data, we have a different utility called Neo4j admin import. That is a tool for production size data. So around 100 billion rows of data points. It's a command line bulk loader, and it's for initial database populations. So you cannot use it to import additional data into your database. It's been designed to scale across CPUs and disk performance, and it's using RAM very efficiently. So this is the tool that you use when you are done with your data modeling and want to actually get that big amount of data into your Neo4j database. All right, I hope I've sparked some interest in Neo4j. Here are the ways that you get started. As I mentioned before, you download Neo4j Desktop. It's free for download. And Neo4j browser is included in the Neo4j Desktop. We also have a sandbox that I'll mention a bit in the next slide. And for connecting to Neo4j, we have official drivers, and we also have community-supported drivers. And there is a large amount of webinars and tutorials. And as I've said before, we have a very active community and frequent meetups around the world. So final word, I want to advertise a bit about our Neo4j Sandbox. If you prefer to not download software locally, you can get a sandbox that we're hosting for you. And you can make it empty to create your own data, or you can get it preloaded with one of these use cases. As you can see, there is a variety, both business use cases and other use cases that are very, shall we say, timely with what's going on in the world right now. All right, that was everything that I had to present today. I thank you for participating, and feel free to send any questions that you have to me.